Hello, everyone, and welcome to our first video on Unit 3.3, where we're now going to understand why we waited until Unit 3 to talk about inverse functions instead of not putting that at the very beginning when we started talking about functions. So, y equals b to the x, so the exponential functions that we had, they're one to one, and as such, they have inverse functions. But what are they? How would we find them? Those are all great questions, and that comes to our first definition. The logarithmic logarithmic function with base b for b greater than 0 and b not equal to 1 is denoted y equals log. So you just write log and then a subscript b of x. I mean, you could also write f of x is equal to log base b of x, but that's how we define it, and that's how it's denoted. And it's defined by if you have y equals log base b of x, then that comes from the exponential version of it, which is going to be b to the y is equal to x, which seems kind of weird. It's kind of like a definition based on a definition. But this is the logarithmic form, and this is the exponential form. So let's digest that for a second. What exactly do I mean? How does this make it like how is it defined this way? If you're trying to find a log value of something, so like log base 5 of 3, you would want to convert it to exponential form to find out what that value would be. So a logarithm is defined based on the exponential function with the same base. So the notes, therefore, is that by definition, that means that logarithmic functions and exponential functions are inverses of each other. That is to say that if you compose them, you get something like b to the log base b of x, and that would just be x. We'd see that the b and the log base b, the the exponential base b and the base of the logarithm end up canceling each other out essentially, and that's just one version of it. But you could also have that log base b of b raised to the x is going to be equal to x because here the log base b and the exponential base b cancel out. So in fact, you could actually generalize this, and this is the better thing. So the generalization is that b raised to the log base b of a blue box is equal to the blue box. I know that doesn't really look like a blue box, but it's kind of like an oblong shape, but whatever. So the exponential base and logarithmic base will cancel out, and you'll just get whatever on the inside. And then by a similar situation, log base b of b raised to a red triangle, the log base b and the exponential base b, they both cancel out and give you just the inside of the exponential function. So this is not going to be super useful right now, part two, like this second note, but it is a good way to think about how inverses work. And this will become especially useful in Math 127 when you start talking about inverse trig functions. So with an exponential function, since they're inverses of each other, but like an exponential function, it takes in an input, it takes in an exponent and then spits out a number. Whereas the logarithm takes in a number and spits out an exponent. So it does the opposite operation. That'll be used like because it's an inverse. So now this little trick here to try and memorize this, it can be a little bit tedious. I didn't learn this until I was in grad school. So one of my students taught me this actually, and I've been using it ever since because it's a very, very good way to be able to convert between the two forms. So I'm going to write them back and forth here. So y equals log base b of x. And then on the other side, I'm going to write b to the y is equal to x. That's the logarithmic and the exponential form. If you want to go from logarithmic. So I'm going to do this kind of weird double-ended arrow where one side is in red and the bottom side is in blue. No, I want that to be parallel, not the same line. So if you want to convert from logarithmic form to exponential form, the student called it the curly Q. And so you start at the base, move across the equal sign, and then back over it to the only other variable left. So b raised to the y is equal to x. Start at the base always, no matter which version, because if you want to go from exponential form to logarithmic, you start at the base, move across the equal sign, and then move back over. And you've got log base b of x is equal to y. So you can convert between the two forms with this little trick. Start with the base, move across the equal sign, and then back over it. That will always work, and it's a very, very useful tip to know. Then the last little note is about the two special bases. Now, we've talked about E before, the natural base, E. Because it's so commonly used, instead of writing log base E, is denoted ln. It looks like a capital IN online because our capital L's and our capital I's and our lowercase L's look very similar in text. But that's an ln, and that stands for the natural log. And then if you have a base 10 logarithm, that is, you've got log base 10, and it's denoted just log, no base at all. And that's the common logarithm. So if you see ln, that means that the log base is e, and if you see just log with no number, that means that the base is 10. The only reason for this that I can think of is the tried and true statement that mathematicians are very, very lazy, and we don't like to write more than we do when we have to. And I am assuming it's because natural log and common log get used so frequently in mathematics that we just got sick of writing log subscript e and just decided to write ln. I mean, you save yourself you save yourself two pen strokes. So it's slowly but surely preventing carpal tunnel. Either way, just remember that natural log is ln instead of log base e, and common log is denoted log, not log base 10. The two most important notes from here, honestly, are note 1 and note 3, especially note 3. I'm even going to put a star next to it just to say this is the best tool to remember. So let's go ahead and convert between logarithmic and exponential form. In this first example, example 3.3.1, we're going to fill in the missing pieces. So with this first one, we're given the logarithmic form and we want the exponential form. So we'll start at the base, move across the equal sign, and then back over to give you 2 to the third is equal to 8. Now the next one is a common log, right? That's a common log. So there's an implied base 10 there. So we'll start at the base, move across the equal sign, then back over. We'll have that 10 to the 7th is equal to x. And you can write it as 10 to the 7th equals x or x equals 10 to the 7th. It really does not matter. It's just a way to, like the equal sign, it doesn't matter which way you got. Anyways, this time we're given an exponential form and we want to convert it to logarithmic. Regardless, we start with the base, move across the equal sign, and then back over. So you're going to have log base 8 of 64 is equal to 2. The next one, this is the natural log, which is log base e. So we can just imply that e is there, move across the equal sign, start at the base, move across the equal sign and back over. So we have e to the negative 5 is equal to y. Now we're given exponential form. We start at the base, move across the, wrong type of font. Move across the, start at the base, move across the equal sign, back over. You've got that log base 1/4 of 6 is equal to x. Couple more. 10 to the 7 is equal to 10 to the w. So start at the base, move across the equal sign, then back over. You've got log base 10 of 7 is equal to w, but that's a common logarithm. A common logarithm. So instead of writing it as log base 10, we will just write log of 7 is equal to w. That's the correct version. This next one, we've got e. Remember, e is just a number like any other number. It's an irrational number, 2.71, blah, 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 blah. But either way, it's a number. So we'll start at the base, work across the equal sign, then back over, and get that log base e of 5 is equal to 2t. But remember, that is a natural log. Which is denoted ln. So instead, we should write ln of 5 is equal to 2t. Natural log of 5 is equal to 2t. Last but not least, I did this one. So we're given the logarithmic form, and I'll do red again. Start at the base, work our way across the equal sign, and then over here. Now the question is, does it just go to the 3y? Does it go to the 1? Does it go to... It goes to everything, the inside of the logarithm. So what we're saying is 6 to the negative 2 is equal to 3y plus 1. And so that's how we convert between exponential and logarithmic form. One last thing for this video is dealing with a very, very useful exponent rule, is that if a to the u is equal to a to the v, and remember, these are the same base. This is not going to be true unless they're the same base. If you have two exponentials, both being raised to different values, but they're the same base, then u must equal v. I know that seems kind of left field here for a second, but I'll show you when we do this one. So example 3.3.2. And if you'd like to see a proof of the reason why this is true, please feel free to talk to me. I'm happy to show you at I'm happy to make a video or explain it in a way. But if we can just take it as fact, find the exact value of the following expressions. Now this, without the use of a calculator, but I mean, I can't stop you if you want to use it, especially since a lot of our calculators can do weird logarithm bases nowadays. But if you want to do it by hand to impress people, right? This is a cool party trick. I guarantee you'll be invited back to every party if you show this. True story. Log base 4 of 64. Now, we don't know what this value is off the top of our heads, so we're going to call it y. Don't know the value. Let's call it y for now. Well, I know it doesn't seem like that helps us very much, but it allows us to convert this to exponential form. Then we get 4 to the y is equal to 64. Now, if you know your powers pretty well, you might notice that 64 is 4 cubed. And so what we have is we have 4 to the y is equal 4 to the third. And if we see above, if you have two things with the same base equal to each other, then their exponents must be equal. So this means that y has to equal 3. Or that is that log base 4 of 64 is equal to 3. Let's talk through that one more time because that was a lot of writing without a lot of time to think. So we didn't know what the value was, so we just called it y. You could use x, you could use any variable you want. We're going to convert it to exponential form. 4 to the y is equal to 64. And then I was hoping for a connection between 4 and 64, which there was. 64 is 4 cubed. So instead of saying 4y is equal to 64, I say 4y is equal to 4 to the third, which means that y is equal to 3. But what is y? y is log base 4 of 64. So what I'm saying is that log base 4 of 64 is 3. However, if you use your calculator, I guarantee you will get the exact same answer. So this is a little bit of a dated thing. It's mainly meant that, like the way we're doing it right now is mainly meant as a way to prepare us for unit 3.5, which is going to be talking about logarithmic equations. This is kind of the start of it. So there's a reason to do it this way, but it's not because you can't do it without a calculator. Either way, we'll move on. We'll assume that this is some value y, and we'll do the curly Q thing, which tells us 5 to the y is equal to 1/25th. And so 25, 1 over 25, that's the same thing as 5 to the negative 2. So we've got y is equal to negative 2, or preferably that would mean that log base 5 of 1/25th is equal to negative 2. I should have been boxing in my answer. Next one, we've got log base 10 of 1,000. Remember, that's a common log. So there's an implied 10 down there. We're going to make that equal to y, and we'll start at the base, move across the equal sign, then back over. We get that 10 to the y is equal to 100,000. Now, that's a power of 10, and in particular, that is 10 to the 5th power. Count the number of zeros, and you've got it. 10 to the 5th power is equal to 100,000. And thusly, y is equal to 5, which means that the log of 100,000 is just equal to 5. Two more. Log base 7 of 1 would be equal to y, and then we'll do the little curly Q. We'll start at the base, move across the equal sign, then back over. You're probably sick of hearing me say that already, but I'll be saying it plenty more. You get 7 to the y is equal to 1. That's not a power of 7, or is it? What number do you need to raise? What exponent do you need to raise something to get 1? 0. So this is actually 7 to the 0, right? Because anything raised to the 0, save for 0 raised to 0, that's indeterminate. But any non-zero number raised to 0 is 1. And that is to say that log base 7 of 1 is equal to 0. Last but not least is natural log of 0. But this is actually a trick question. And we can try to do what we've done, and we'll see that why this is a trick question. So that's natural log of 0, but natural log is the log base e, so there's an implied e here. And so we're going to make this equal to y. We're going to assume that it could be done. Then move across the equal sign, back over. You'd get that e to the y is equal to 0. However, that's not possible, because e to the y is always greater than 0. In fact, I'll say because b to the x is always greater than 0 for any base b and all x. So no matter what you plug into an exponential function, it will always be strictly positive if we remember correctly. So it cannot be 0 and it cannot be negative. So this is a trick question. So it's not possible. Doesn't exist. And then that'll do it for this video. But if you want to, there's a cool challenge problem of log base 9 of 243. My hint to you is that what is a common base between 9 and 243. Utilize that if you'd like to do this problem. You'll find the answer should be 5 halves as it says in the answer. That'll do it for this video, and I'll see you guys on the next one.